The last major topic that we want to introduce today is the concept of locality. There are actually two kinds of locality that we care about. The first is called temporal locality, which refers to the idea that frequently accessed items will continue to be accessed in the future. And so the core theme here is that repetition is common in computing. The second kind of locality that we care about is spatial locality, which kind of revolves around this idea that nearby addresses are more likely to be accessed soon. And so the theme here is that sequential access is common. And we care about this because programs with good locality are going to take better advantage of our memory hierarchy, and they're going to run faster than programs with poor locality. So let's think about this a little bit. So assume that the last three memory locations accessed in a program were in hex 438, 43C, and then 440 in that order. So what is the address in hex that is most likely to be accessed next? So take a second and see if you can identify this. So hopefully if you were able to do the arithmetic in hexadecimal, you'll see that each of these addresses is 4 bytes apart. So for instance, maybe this is an integer array of 32-bit integers. Regardless, if we are accessing memory in this pattern where every access is 4 bytes after the previous one, that means that location again in hex 444 is going to be the one that's most likely to be accessed next. So this brings us to the lesson here, which is that using predictable access patterns exhibits spatial locality. So for instance, stride 1, which is strictly sequential access, reading each byte one at a time. Or stride k, where you're trying to access things every k elements at a time. This is closely related to how arrays are laid out in memory. Are they laid out row by row, which is referred to as row major, or are they laid out column by column, which is column major? And so if your program uses predictable access patterns and accesses things sequentially, this allows the computer to prefetch the things that the program is going to need next. The system can predict what's going to be needed and can go ahead and preload it before the program actually needs it. Reusing values over and over again exhibits temporal locality, and this allows us to keep those things, the things that are going to be used over and over again, in a high level of the memory hierarchy, so that they're going to be very fast to access. So let's think about this again with another question. So which of the following are going to generally exhibit good locality? Which of these things are going to have good performance given what we've learned about the memory hierarchy? So take a second and think about these, and this is a choose all that applies, so any number of these might be correct. So pause the video and see if you can identify which of these are generally going to give us good performance in our program. Okay, so normal code execution exhibits good spatial locality because all the instructions are executing in sequence. And so generally it will be easy for our computer system to identify which instructions are going to be executed next because they're just going to be the ones that are next in memory. Correspondingly, long jumps exhibit poor locality because you're going directly from one instruction to another instruction that's far away. And so it's going to be difficult to predict where that is, and the system may have to, for instance, if it's on a magnetic hard drive, this system may have some latency associated with moving to that new location. This includes things like function calls because, of course, you're moving from one place in the program to another. Loops actually exhibit both temporal and spatial locality because the statements in the loop body execute repeatedly, which gets you temporal locality, and in sequence, which gets you spatial locality. And of course, shorter loops are better because the shorter the loop is, the better the chance that it's going to fit in a higher level of the cache.